Sir, is my screen sharing enabled?
Yeah. Yeah.
Okay. Okay. So, in terms of conductive heat transfer, my thermal resistance is basically given by RTH. Like in terms of conductive heat transfer, what is the formula for my like what is the formula for my thermal resistance for conductive heat transfer? It is RTH is equal to L by Ka, or here I am writing as delta by Ka. And in terms of convective heat transfer, what is my formula for thermal resistance? So thermal resistance is basically given by what? So thermal resistance in case of convective heat transfer is given by 1 by HA, where H is the convective heat transfer coefficient and A is again the area normal to the area normal to the interface, right? And then we are having radiation. Okay, so whenever we are having radiation, so in case of radiative heat transfer, my thermal contact resistance is basically given by what? My thermal contact resistance is basically given by 1 by HRA, right? What is HR? HR is the radiative heat transfer coefficient. And if you want to define HR more precisely, then HR is basically defined as sigma B into F12 T1 square plus T2 square into T1 plus T2. What is this T1 plus T2 and T1 minus T2? See, suppose if from one particular surface, the heat is getting transferred via radiation mode, right? If from one particular surface at a temperature T1 to at a temperature T2, my heat is getting transferred, my heat is like getting transferred via radiation mode, then in that particular case, since this radiative heat transfer is governed by what? It is basically governed by Stephen Boltzmann law. So, but to reach this particular surface, again, it might be having some medium, right? And it might be having some geometry. So this formula F12 is coming from where? It is coming from my geometry of my specimen, through which my heat transfer is getting, like through which my heat transfer is happening, heat transfer is happening via radiation mode. Okay. So how do we derive at this particular formula? So this particular formula is given as Q dot radiation is equal to, sorry, yeah, so Q dot radiation is equal to HRA T1 minus T2 equal to A1 F12 sigma B T1 to the power 4 minus T2 to the power 4. Okay. What is the sigma B? It is the Stephen Boltzmann constant. What is the value of Stephen Boltzmann constant? The value of Stephen Boltzmann constant is 5.67 into 10 to the power minus 8. Okay. And what is this F12? This F12 is basically the view factor. View factor is also important. Many questions are coming nowadays in GATE on the basis of view factor only. So if you will solve, if you will equate this equation and this equation, you will ultimately get this particular thing. Okay. Now, we would be talking about the cases of we will be talking about the cases of steady state heat conduction, right? With internal heat generation. Okay. So we would now talk about the case of steady state heat conduction with internal heat generation. Okay. So suppose there is an internal source which is continuously generating heat. So with the internal heat generation, we would talk about the steady state heat conduction. And this, like what is the first case? The first case will be the wall having different temperature at two different phases, right? Suppose we are having a slab. Suppose we are having a slab and the slab is like we are having a temperature T1 and then we are having a temperature T2 and the value of internal heat generation is Qg, the thermal conductivity of the wall is K. So if you are having internal heat generation and it is a rectangular slab with the two different temperatures at two different phases and the thickness of the wall is delta. So in that particular case, what equation to use? We saw in case of one-dimensional heat transfer with internal heat generation, we are basically using this format. What? Del square T plus Qg by K is equal to 1 by alpha del T by del tau. Okay. Now, since it's what to say, it's a general, it is a format of a general heat conduction. Now, since it is a steady state heat conduction, so this particular factor becomes zero. And if this particular factor becomes zero, since it's a steady state heat conduction, then my equation would become del square T plus Qg by K is equal to 0. Okay. And how do we write it? We are basically writing then finally the temperature variation, the variation of temperature across the wall after integrating and differentiating it. I am not showing the derivation because in GATE examination, you directly apply the formula and get the answer, right? So it is equivalent to Qg by 2k into x square plus C1x into C2, right? So where C1 and C2 are the integration constant and we can apply the boundary condition. And after applying the boundary condition, what can we basically write? Like, suppose I want to know that what is my heat content at a particular distance x. Okay. Like what is my heat content at a particular distance x from the wall which is having a from the side of the wall which is having a temperature T1. तो इस x डिस्टेंस पे मेरा कितना टेम्परेचर बैठेगा तो वो मैं इस इक्वेशन को सॉल्व करके निकाल सकता हूं एंड आफ्टर अप्लाइंग the boundary condition and putting the values of C1 and C2, what is the final thing that we get? The final thing that we get is T is equal to T1 plus T2 minus T1 into x by delta plus Qg by 2k into delta x minus x square. Okay. So this delta is the thickness of the wall. This Qg is the rate of heat generation or per unit volume, how much heat is getting generated. This K is the thermal conductivity of the wall. And this X is finally what? This X is the distance from the side T1 up to which, like the distance at which I want to know what is my temperature inside the wall, right? Okay. So how the variation is across the wall having two different temperatures. Like suppose here I am having T1 a higher temperature and I am having T2 the higher temperature. So the heat distribution is parabolical. It is something like this, right? In case of a steady state heat transfer with no internal heat generation, the heat distribution is linear. But in case of what to say? In case of heat transfer which is steady but we are having a internal heat generation source, then my heat distribution profile is something parabolical. Is it clear? Okay. Now you see, we are here talking about the cases where my thermal conductivity is constant. But all of us know that in some materials, there is a huge variation in thermal conductivity with respect to temperature. So how will my graph look like in those materials, right? So in those materials where there is a huge difference, right? Where there is a huge, like not a huge difference, but where the thermal conductivity basically changes. The thermal conductivity basically changes with respect to temperature. So in those materials, my heat distribution is given by, like, if you want to actually draw the heat distribution across the wall, then it is given by this particular profile analysis. ठीक है? So how do you define the variation of thermal conductivity with respect to temperature? So it is defined by this. K is equal to K naught into 1 plus beta T. What is K naught? This K naught is basically the thermal conductivity at 0 degrees Celsius. And what is this beta? This beta is a constant depending on the type of material. Okay. So this beta basically depends on type of material. Depends on material. So this is the variation that you will get in case of materials having variable thermal conductivity. Okay. So now here we talked about only the rectangular slab. What about the case of a hollow cylinder? See, in case of a hollow cylinder, whenever we are dividing the case, in case of a hollow cylinder, we must remember one thing. In case of a hollow cylinder, we must remember that we are having a logarithmic. Match the following में आता है भैया. We are having a logarithmic temperature variation with respect to radius. Okay, so we are having a logarithmic temperature variation with respect to R. So we are having a logarithmic temperature variation with respect to R in case of a hollow cylinder. And what are my assumptions? My assumptions are basically the material is homogeneous and isotropic. Heat is getting transferred radially. We are having no internal heat generation. It is a steady state heat transfer. And last but not the least, the value of thermal conductivity is constant. So in case of a hollow cylinder, we can draw it like this. Okay. So it is having a R1, it is having a radius R2, the inner radius is R1, the outer radius is R2. And if you really want to know the heat distribution among radially, so heat distribution, suppose it is having a temperature T1, it is having a temperature T2. So we are having a logarithmic heat distribution between two surfaces, that is T1 and T2. Okay. And how do you exactly represent it? The conduction heat transfer through the hollow cylinder is basically represented by Q is equal to T1 minus T2. Suppose if T1 is higher than T2, then Q is equal to T1 minus T2 ln R2 by R1 divided by 2 pi KL. I know it is having this formula is coming out from a derivation, but gate में derivation important नहीं होता है. अगर आपको formula direct पता है 2 मिनट में आंसर आ जाएगा. Okay, so please remember this formula for case of a hollow cylinder having with no internal heat generation and one-dimensional conductive heat transfer, and where the thermal conductivity is basically constant. Now there might be cases, ऐसा मतलब जैसा गेट में 3 बार पूछा भी जा चुका है ये सवाल. ठीक है, ध्यान से देखना इस सवाल को, मतलब इस केस को. So what is there? So with, see, suppose between the axis of the cylinder some fluid is flowing, right? And this fluid is basically transferring heat to the inner wall of the cylinder via convection. And from the inner surface of the cylinder to the outer surface of the cylinder, the heat is getting transferred via conduction, right? So in case of a hot fluid carrying hollow cylinder exposed to ambient atmosphere, आपके घरों में भी मिलता है, आपको पता है जो आपका हीटर जो आपका इंडिकेशन देता है ना कि अरे 20 डिग्री गर्म हो गया, 25 डिग्री गर्म हो गया, when it finally comes out of the tap water, it is actually at a temperature of, let's say, hardly 22 to 23 degrees Celsius, but heater is showing 25 degree or 30 degree. So during when the hot fluid is basically carrying the hot water through the pipe, since that hot fluid carrying hollow cylinder is exposed to the ambient atmosphere, my heat is continuously getting lost via convection through the inner surface of the pipe and conduction to the outer atmospheric surface, right? So suppose if the length of the pipe is L, if the length of the pipe is L, then this hot fluid carrying hollow cylinder exposed to atmospheric, we are drawing a thermal circuit. So this thermal circuit is what? One thermal circuit is when the heat is getting transferred from this hot fluid to the inner surface of the cylinder, right? So let us name it as RTH1. What is RTH? Again, thermal resistance. And how can we define another circuit? The another circuit is basically defined as when the heat is getting transferred from the inner surface of the cylinder to the outer surface of the cylinder, and that is given by RTH2. And the third is the RTH3, like the heat is getting transferred from the outer surface of the cylinder to the ambient atmosphere, right? So this is the circuit. So now, how can we define RTH1, RTH2, and RTH3? So RTH1 in conduction mode, we have written now, RTH1 in conduction mode is represented by what? RTH1 in conduction mode is represented by 1 by HA. Okay. So here RTH1 is represented as 1 by H1 into 2 pi R1L. And RTH2 is equal to ln R2 by R1 divided by 2 pi KL. Okay. And RTH3 is basically represented by 1 by H2 into 2 pi R2L. Okay. So these are the three, which is like, these are the three series conductance, right? So they will be added side by side. And let's take a special case. The special case is the last case of today's topic is, the last case of today's topic is, we are having a solid cylinder having a internal heat generation, right? The uranium fuel rod case. ये बहुत इंपॉर्टेंट है यार ये केस, और ये केस आपका आने की चांसेस बहुत ज्यादा है, तो इसे ध्यान से देखना. द यूरेनियम फ्यूल रॉड केस, वेयर द यूरेनियम फ्यूल रॉड इज हैविंग अ लेंथ ऑफ L and it is having a radius R. So across it, how we are having an internal heat generation QG. So across this, how the temperature difference is, how the temperature variation is taking place, it is TW plus QG by 4K into capital R square by small r square. What is small r square? Suppose I want to know what is my temperature here at a distance R from the center of the uranium fuel rod. So at a distance small r from the center of the uranium fuel rod, what we can write at the center of the uranium fuel rod, we can write it as this. So it is a parabolical. It is a para, ये भी important है, match the following में आता है. It is a parabolical heat, match the following, या उसमें MCQs में आएगा. So parabolical heat variation in case of a solid cylindrical fuel rod having an internal heat generation. And suppose I want to know the temperature at a particular distance small r, we can write it as TW plus QG by 4K small capital R square divided by small r square. And what is the maximum temperature? The maximum temperature is definitely temperature at the outer surface of this uranium fuel rod. So the maximum temperature is given by TW plus Qg by 4K into R square. Okay. So guys, I guess in this 1 hour session, we were able to learn some good things. I know many more concepts are left in this various modes of heat transfer, but it is not possible to cover in a single class. So I tried to cover the maximum that I could. So we guys will try to cover more during our next classes, right? And our next class is gonna take place on which date? Vishal sir, our next class will possibly take place on which date?
Let's plan after 7th of January. So we will discuss about it, and we will inform to all of the students who will be interested.
Okay, sir.
Okay. Yeah. Thank
Okay,
you so much
so yes,
for
sir.
giving your
Let's
valuable
end this
time,
class.
and wish you a very, very happy New Year.
Thank you, sir. Okay, okay. Okay, sir.